This is lesson 2.2, the mass spectrometer. So why do we use a mass spec? A mass spec is a really big machine that's used to mass different isotopes and determine their relative abundance, or their percentage.
What happens if you have something like this, and you want to find out if something like this is inside? Obviously you can't tell just by looking at it, but if you separate things out, the answer becomes clear. Scientists have the same problem. How do you know if there was once water on Mars? Or, for that matter, life? Obviously you can't tell just by looking at pictures of Mars, but scientists think the answer may lie hidden in tiny molecules in Martian soil. So how do you take apart a molecule to see what's inside? Luckily, scientists have a tool to do just that. It's called a mass spectrometer, and it lets us take an extremely close look at whatever we're studying. And even though Mars immediately comes to mind, mass spectrometers are used in multiple NASA missions. They're also used in labs for hundreds of scientific purposes. But the important question is, how does it work? Today we'll be looking at a special kind of spectrometer called the quadrupole mass spectrometer. It's called this because of the 4 long poles that make up the center of the instrument. So say you have a sample that's been turned into a gas, and you want to find out if it contains certain things. The gas is sent into the mass spectrometer, first hitting a piece called the ion source. Here, a stream of electrons hits the molecule, breaking it into fragments and giving each fragment a charge. Next, the fragments enter what's called the analyzer. Here, they're separated based on their mass, and the analyzer is tuned so that only the fragments we want to see make it all the way through. Everything else flies off in a different direction. After this, the fragments hit what's called the detector, and scientists record the data. If you're looking for more than one kind, the analyzer can scan across a range of fragments, building up a record of not only what kind, but how many. Once you have these results, called a mass spectrum, you can verify that your sample in fact contains what you're looking for. And here, the real work begins. The mass spectrometer is a powerful tool, and by taking many samples, looking at the results, and studying what we find, scientists can work to discover not only the secrets of water and life on Mars.
So how does a mass spec work? Well, there's a few steps you have to memorize. This first step is vaporization. So the first thing you do is inject your sample into the mass spec where it's vaporized or turned into a gas. The second step is called ionization. Once you inject your sample, the atoms are hit with high energy electrons, which knock out more electrons, producing positive ions. So if this is your sample, you're hitting it with electrons to make positive ions and knocking out electrons. The third step is acceleration. In acceleration, those positive ions that you created are attracted by negatively charged plates, which pull the ions along and accelerate them through an electric field and through a hole in the plate. The fourth step is called deflection, which is where accelerated positive ions are deflected by a magnetic field placed at a right angle to their path. And the amount of deflection is proportional to their mass to charge ratio. The smaller the mass of the ion, the more deflected they are. And the ions with higher charge are deflected more as well. The fifth step and the last step is called detection, where the positive ions are detected and sent to a recorder. And the strength of the signal in the recorder measures the number of ions with that specific mass to charge ratio. So remember that the relative atomic mass is always compared to carbon-12, and the relative atomic mass of carbon-12 is 12.011 AMU. So here's an example of a mass spectra, and on the horizontal axis you can see the mass to charge ratio, and the vertical axis always shows you the relative abundance of the ions. So here's a mass spec of boron, and the question asks you to find the average atomic mass. Well, if you remember, the formula for average atomic mass is the sum of the mass of the isotopes times the relative abundance. So here we have 2 isotopes, 1, 2, so we need 2 sets of parentheses. The first has a mass of 10 and the second 11. And now we need to find the relative abundance, or percentage. So if you look at the total, 100 plus about 25, we can see that the percent of the isotope with mass 10 is going to be 25 over 125, which is the total. So when you divide this, you get 0.20. So because they have to add up to 100%, you know that this one must be 80% or 0.80. And so when you plug these into our formula for relative abundance, we get an average atomic mass of 10.8 AMU. Here's another example. Here's the mass spectrum of chlorine. Find the average atomic mass. Again, we have two isotopes, so two sets of parentheses. The mass of the first is 35, and the mass of the second is 37. And this time, they don't give you numbers on the left, they give you 3 to 1, meaning that the height of this peak is 3 to 1. So 3 divided by 4 is 75%, and 1 divided by 4 is 25%. Change those to decimals, and when you plug them in, you get an average atomic mass of chlorine of 35.